What is going on, guys? Welcome back to another video. So in today's video, I'm going to explore how a modern processor runs instructions. And spoiler alert, it's different from a primitive processor like the ones we've seen in my playlist SI2AI. So if you haven't seen that playlist, go to the link in the description. It has all the way from primitive NAND gates up to how AI works. So yeah, if you did see that playlist, you might wonder in the assembly section why the processor just runs a bunch of instructions sequentially and just idles half the time, because it's going to be doing stuff only at specific stages, but all the other stages just kind of sit there. And yeah, a lot of engineers wondered about that as well. So processor designers changed how processors work throughout the decades, and now your modern computer processor is way more complicated than a primitive model that we've seen there. But today I'm going to give you guys the basics, so hopefully you guys will appreciate and understand how a modern processor works compared to a primitive one. So let's get started with this question. So this question here, we have 5 assembly instructions, all doing just ALU operations, and we want to see how a modern processor executes them. So first thing we're going to do is we're going to recognize the fact that modern processors have over 200 physical registers, and that's by no mistake because they're going to take advantage of something known as register renaming. So let's see what a physical register is. First of all, just to mention, architectural registers are the ones that we use. For example, R8, R9, RAX. So these are specified by the x64 standard. This just tells programmers that you can just use these processors and you should just assume it works. But the processor designers, they're not prevented from adding their own registers. They just have to make sure that the ones that x64 specifies works, but they also can just implement it however they want. So the processors are going to be called physical registers. So these are the registers actually stored in hardware. So these registers right here are going to be different, and there are a lot of them. So in x64, there's only about a few dozen registers if you count floating point. With physical registers, as you can see, easily up to 200 to 300 registers depending on the architecture, like modern Intel or AMD. So we're going to see how the processor converts these. First, let's just see what processors, what registers, a lot of processor register terminology there, but what registers are in use here. So we have R8, R9, R11, R10. So it looks like just from R8 to R11. So we're just going to list out all the architectural registers used, and there we go. 5 of them, or 4 of them, can't really count today. But basically, we're going to translate them all into a physical register. So physical registers, they're denoted using this X notation to kind of differ from the R notation. So we're assuming this processor is just starting for the first time. So the first physical register is just like 1. And then we're going to do x2, and because all the physical registers have nothing in them, we can just assign them down sequentially like so. So now we've completed our mapping. Now the processor knows what each architectural register actually maps to. So now let's actually convert these instructions to this new set. And you might think it's just drag and drop replace, but there's a bit more to it. So first, we're just going to substitute R8 to X1, and then R9 to X2. But here's where we can take advantage of the 200 registers. So we're going to actually save this output into X5 because X4 is already used down here. What this allows us is it allows us to snapshot the architectural register, like for example, in this case R9, at different stages in the processor's execution. So here, our R9 is saved in X5. Because in the original, R9 gets modified anyways. It gets ANDed with R8. Now, let's go to the next instruction and see. So the next instruction involves R11, which is just X4. But this time, instead of R9, we use X5. See how X5 gets substituted from here to, or I guess from here to here. So now we're using the version of R9 that's in the AND queue's final output. Now we're once again saving this to a new register, X6. So this is a new physical register, and once again, this is the representation of R9 at this instruction. we can just keep on going. So add Q, we do R9 this time, but remember R9 is actually X6 now. So we just add X6 to itself, save that to X7, which also still represents R9. So you can see R9 is being updated a lot in at least this example. So now we can do our XOR, and then R9 is X7 now, and then R11 never got changed really so far, so it's still X4. But now it's R11's turn to get changed due to how AT&T syntax works. And now R11 is X8. Yeah. 5, 6, 7, 8. There we go. So this represents R11. And then finally, the sub Q operation involves R8, which is X1, and R10, which is X3. We can save that into X9, and this represents R10. So notice how this gives us a lot more flexibility when it comes to running instructions. Because rather than just normally running them sequentially, we can now use this to our advantage and save stuff in snapshots and kind of do some parallel execution. But before I talk about that, let's first talk about how the out of order processor, which is kind of this whole paradigm here, how that works in its pipeline stages. So first, we take a look at the life of an instruction. So the instruction kind of gets born, or I mean it's stored in the L1 cache. Its first journey is to go to the fetch stage. So this fetch stage just again fetches from the L1 cache, that's it. And then it goes to decode, so this is pretty normal stuff so far. And then it goes to the rename stage. So this stage is the one that we just manually accomplished. The next stage is issue. This we will talk about more later. And then, of course, the next stage is execute. The second to last stage is write. And then finally, the last stage is commit. Let me talk about commit first. But before I do that, just know that write can go to the L1 data cache. So this is actually important, this whole kind of thing right here, because this enables side channels to happen, at least cache side channels. By the way, if you want to know what a side channel is, I'll make a video if this gets enough likes. So yeah, comment below if you want kind of me making a video on what side channels are. But basically, just know that because the L1 data cache gets modified even before the processor is done, you can kind of leak information. That's all I'm going to say. But basically, how this works is once you get through this commit instruction, the processor is telling the entire system that I am fully done with this instruction and the answer is final. This is what I want to give. Anything else in this stage, so this fetch, decode, rename, issue, execute, write, commit stage. So that's like 7 pipeline stage. Any other pipeline stage isn't final. So the processor can do branch prediction, for example. It can look ahead, try to compute because it has a lot of registers, save it, and then realize, oh, it's wrong, so let me just roll back. As long as it doesn't hit this commit stage, it will be fine. So yeah, that is kind of how processors allow very fast execution. So that kind of answers, at least helps answer part of the first question, which is what instructions can the processor issue immediately. So based off the renaming, we're going to assume many single cycle ALUs. So we're going to assume in this architecture, after the issue stage, after the issue stage is the execute stage. So let's say issues here, renames here. So rename goes to issue, and then issue goes to the execute stage, which is the ALU. So we can just assume multiple ALUs just waiting their turn for the instructions to come. And what this does is that it allows one instruction to go to this ALU, and then if they don't conflict with each other, another one can be run as parallel. So now both of them get executed at the same time. And yeah, that kind of speeds up stuff. So in this case, what can we send to multiple ALUs at once? Well, first, let's say at t equals 0, so when this just started, we're at this AND Q instruction right here. We want this to run, so we issue this to, let's say, ALU1. So this instruction goes into ALU1. Now, can the next instruction go into another ALU? No, because of R9. R9 needs to be calculated, so is this, and the only other instruction that can go to another ALU at t equals 0 is sub Q, because this doesn't involve R9. You can see none of these registers depend on the previous 4 instructions. So in fact, this first instruction, if I just enable this 1, 2, 3, 4, 5, the first instruction can go here. This 5th instruction can be ran all at once because the 5th instruction never depends on the first one. And then at t equals 1, now the instruction number 2 can start running. So how we can phrase this is about 2 instructions can be immediately issued. They can immediately run at once, that's 1 and 5. And how many cycles does it take for all of them to run? Well, of course, since 2 can run at the first, the rest depend on each other. It will take 4 cycles for the rest to run. And just to kind of illustrate this whole point of this time thing, technically speaking, I'm using this time term loosely because this isn't actually t equals 0. If you actually want to see the time, I'm going to list it out here. But basically, t equals 0 is when the very first instruction gets into the fetch state. At this point, kind of nothing's going on yet. So then t equals 1, it goes to decode. T equals 2, it goes to rename. T equals 3, it goes to issue. So actually speaking, by the time the first instruction goes to an ALU, we're already at t equals 4 based off of kind of just like this thing. And then t equals 5, we are either writing or rolling back, but there's no branch prediction, so writing. T equals 6, if everything goes well, that's where it will finally commit. So you can do the same for the other 4 instructions. So once again, it has to wait a cycle for it to run because these instructions right here, they kind of depend on each other. So this is where this gets staggered. But notice the 5th instruction, so pretend there's more instructions here, dot, 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 dot. And then 5th instruction, it can get fetched, it can get decoded, it can get renamed. But at this issue and execute step, this is where this comes in. And now the 5th instruction suddenly is running alongside of instruction 1. So this execute is at t equals 4, or I guess cycle 4. And yeah, so this execute instruction is simultaneous with instruction 1, allowing faster execution. And this goes into a lot of different things. For example, how can you write code that takes advantage of this? If you have too many branch mispredictions, that might cause a slowdown because the CPU has to do a bunch of rollbacks. And yeah, so that goes into a lot of modern processor code writing stuff. But yeah, hopefully this kind of shows you the simple, intuitive explanation of why modern processors can run faster but still be correct. So yeah, the correct answer is what instructions can run. The instructions 1 and 5. So the first one and the last one can be ran all at once. And then how many cycles does it take? It takes 4 cycles. So yeah, hopefully you enjoyed this video. If you did, leave a like and subscribe, and maybe I'll cover side channels or branch predictions. And yeah, I'll see you in the next one.